Okay, so now we're going to continue our discussion of monosaccharides. We've seen the structure of glucose. It can also be called dextrose. This is the sugar found in our blood and the most abundant of the monosaccharides. Normal blood glucose levels are between 70 and 110 milligrams per deciliter. So if you go to the doctor and have your blood glucose checked, it should fall into that range. Excess glucose is stored as a polysaccharide known as glycogen, or it can also be stored as fat. Insulin, you probably know, regulates blood glucose levels, and it does so by stimulating the uptake of glucose into the cells in our tissue or the formation of glycogen. And patients with diabetes produce insufficient or no insulin, so they are unable to regulate their blood sugar levels. So they must monitor their diet and or take medication or insulin daily. So the common monosaccharides you're responsible for are glucose, galactose, and fructose. We've seen both glucose and fructose. And I want to point out that if we locate the hydroxyl group that is furthest from the carbonyl group in these molecules, it's going to be the one on the carbon on C5, and these hydroxyl groups are all on the right, so that makes them the D enantiomer of these molecules. Additionally, there's a relationship between glucose and galactose. If we look at the location of the hydroxyl groups on carbons 2, carbon 3, we see they are in the same location. But when we look at carbon 4, we see that the hydroxyl group in galactose is on the left side, not the right side. So we can say that galactose is a C4 epimer of glucose. So that tells me at C4 the hydroxyl groups are on opposite sides. There is one other epimer of glucose, and that's mannose. It is a C2 epimer. Galactose is one of the components of the disaccharide called lactose. Patients with galactosemia lack an enzyme needed to metabolize galactose. So this causes the accumulation of that molecule and contributes to cataracts and cirrhosis. Fructose is one of the components of the disaccharide sucrose. So another term, sucrose, that you've been exposed to already. I believe we talked about reducing sugars, and sucrose is a non-reducing sugar. Fructose is also the ketohexose found in honey and almost twice as sweet as table sugar with the same number of calories per gram. So you get more bang for your buck with if you use honey instead of sugar. So we have been looking at these specific molecules. Now we're going to look at a reaction of a monosaccharide or an aldehyde sugar. And they can react with alcohols. And when they do that, they form what is called a hemiacetal. So here we have an aldehyde. So that's the aldehyde head. We have our generic alcohol group. And when these react with one another, we get this linkage Okay, so we have the hydroxyl group, and I'm trying to reorient myself here, and the oxygen attached to that. So this oxygen is found here. So they link through that, and we get this type of linkage here. So when the aldehyde and an alcohol are in the same molecule, they can form a stable cyclic hemiacetal. So what is meant by that? If you think about it, all of our carbohydrates, have alcohol moieties and aldehyde moieties, correct? Absolutely. So this is just a generic pentanal that has a hydroxyl group on carbon 5. So that means that a reaction can occur between that hydroxyl group and the carbonyl carbon. And when that happens, we form a cyclic molecule. So we have that, this, of course, is here. So it starts folding around, and the hydroxyl group and the carbonyl group react, and we form what's called a hemiacetal. And this is the group associated with that. So the carbon atom that is part of that hemiacetal group forms a new chiral center, and we call that an anomer. So, or in other words, anomeric carbons. So we have two, and there are two possible positions for the hydroxyl group that is attached. So when the hydroxyl group is in the down position, it's an alpha anomer, and if it's in the up position, it's a beta anomer. Okay? So alpha and beta, and you should be able to recognize those two forms. So let's take a look at the cyclization of glucose. So we first have to determine which alcohol is going to be used to make a 6-membered ring. Okay? And this carbon number 5 is in the right position to do so. So this is the hydroxyl group that is going to participate in the reaction. And it's common to teach someone how to cyclize these molecules by laying them on their side. Okay, so all we're doing is tipping that molecule over onto its side. So now the hydroxyl group in C5 is on the bottom. Okay, and this corresponds to this hydroxyl group. Okay, so we just lay it down. After we lay it down, this is going to start swinging around until we get a loop. So we've got a loop, and this 6 carbon is in the up position. Okay. So here's our hydroxyl group on C5, and it is going to react with the aldehyde head group. Whoops, I went too fast there. And unfortunately, when I'm recording, I can't go back. So I will just, well, actually draw the couple, no, they're right here actually. They're shown here as well. So these were the two possible structures that would come from that cyclization when we have the hydroxyl in the up position or beta, or down position for alpha. But what this slide is actually addressing is the fact that all three of these structures exist in equilibrium, and that equilibrium is called mutarotation. So the molecule is constantly opening and closing, and as a result, if we took a sample of glucose, we would find about 30% of those molecules would be the alpha enantiomer. There's just a little bit of the open ring, and then the beta form of glucose is in the largest percentage, or percent, which is 63%. So ketones like fructose can form 5-membered rings with the same two enantiomers. So here we have the fructose in its straight chain. The hydroxyl group on C5 is furthest far enough away, and remember it has to have a chiral center as well. So that's why we can't use carbon 6. But unlike the aldehydes, with the carbonyl group on carbon 1, ketones or ketosis or fructose has that carbonyl group on carbon 2. So what we end up with here is a 5-membered ring. Same process, we would lay that fructose down flat on, or draw it flat, or laying down, and that hydroxyl group on C5 interacts with carbon 2, and we get 5-membered rings. So we have one, wait, where are we here? 1, 2, 3, 4, 5. Yeah. Little different shape. This one actually kind of looks like a tilted house, so to speak. But same naming scheme here with respect to the position of the hydroxyl group on the anomeric carbon, and it's either in the alpha position or the beta position. So alcohol, like alcohols, and previous discussion of aldehydes, oxidation and reduction can occur depending upon what the functional group is. The carbonyl group of an aldose can be reduced to a primary alcohol if we use H2 and palladium. So here we have an example of that. So remember, when we add H2, we are adding across a double bond, and so we're reducing the number of carbon to oxygen bonds, so this is reduction, and what we end up with is with a hydrogen added to each this carbon and this oxygen. So now we have an alcohol head group. Okay. So this is an alditol, OL for alcohol. We can also oxidize that aldehyde head group, and in this case, the example is using Benedict's reagent, which you have already used in labs. Remember, ketoses cannot be readily oxidized. So we have not been able to observe oxidation of ketosis and won't. But here we have glucose, which of course has that aldehyde head, and the copper ion from the Benedict's reagent, and we have hydroxide ion as well. And this is then oxidized, or we increase the carbon to oxygen bonds and that carbon to produce a carboxylic acid. And when we name that, it's called gluconic acid. Plus you get this indication of the oxidation having occurred when you see that brick red precipitate forming.